The North Atlantic, January 16, 1943. The Liberty ship SS Schenectady sat peacefully at the outfitting dock in Portland, Oregon, her hull freshly painted, her holds empty, her crew preparing for the maiden voyage that would never come. At 16:55 hours, a sound like a rifle shot echoed across the shipyard. Workers looked up from their stations to see something impossible unfolding before their eyes. The Schenectady was breaking in half. Not from a torpedo strike, not from a collision, not from any external force whatsoever. The 441-foot vessel simply cracked open like an eggshell, the fracture racing across her deck at supersonic speed, tearing through steel plates as if they were paper. Within seconds, the ship's hull had split completely, the two halves sagging grotesquely, held together only by the keel at the bottom and a few twisted steel plates. The Schenectady hadn't even left port. She had never carried cargo, never faced a storm, never been tested by combat. She simply broke apart while sitting quietly at dock on a calm winter day. 50 miles away, the Liberty ship SS John P. Gaines suffered an identical failure 3 days later. Then the SS Esso Manhattan, a T-2 tanker, split in two while sailing in calm seas. The SS Pontiac cracked completely through her deck. The list grew longer each week. Ships that should have been invincible were fracturing without warning, some catastrophically, some fatally. American shipbuilding, the industrial miracle that was supposed to win the war, faced its greatest crisis. And German engineers, watching intelligence reports flow in from across the Atlantic, couldn't hide their satisfaction. American welding technology, they noted in technical assessments, was proving to be exactly the disaster they had predicted. The Americans, in their characteristic rush for speed and volume, had abandoned proper shipbuilding techniques. They had replaced time-tested riveting with crude electric arc welding, prioritizing production numbers over structural integrity. Now they were paying the price. What the Germans didn't know, what nobody knew in those desperate months of 1943, was that American metallurgists and engineers were about to solve a mystery that had baffled the entire world. They would discover a phenomenon so fundamental to material science that it would revolutionize not just shipbuilding, but every industry that worked with steel. And in the process, they would save an entire fleet, win the Battle of the Atlantic, and prove that sometimes the crudest solution, properly understood, becomes the most sophisticated answer. This is the story of how American welding went from laughingstock to revolution, how catastrophic failure led to scientific breakthrough, and how 2,500 ships that should have sunk instead carried the Allies to victory. The Liberty ship program represented American industrial ambition at its most audacious. In 1940, as Britain stood alone against Nazi Germany, the U-boat campaign was strangling maritime commerce. German submarines were sinking merchant vessels faster than British shipyards could replace them. The United States, still officially neutral, needed a solution. Henry Kaiser, an industrialist with no shipbuilding experience, proposed something radical: standardized merchant ships. Built in sections using prefabrication techniques borrowed from automobile manufacturing, assembled with electric arc welding instead of traditional riveting. The design came from a British pattern, the Ocean class, but Kaiser's vision was pure American mass production. The numbers seemed impossible. Traditional shipyards took 8 to 12 months to build a cargo vessel using riveting. Kaiser promised to deliver completed Liberty ships in 70 days, then 60 days. Eventually, the Richmond Shipyard No. 2 would complete the SS Robert E. Peary in just 4 days, 15 hours, and 29 minutes from keel laying to launch, a record that stands unbroken. By 1943, 18 American shipyards were producing Liberty ships around the clock. Workers with minimal experience operated equipment they'd learned to use weeks earlier.
Women who'd never seen a shipyard before Pearl Harbor now operated massive cranes and welding equipment. The production numbers were staggering. 3 ships per day at peak output, 2,710 vessels completed by the program's end. But something was terribly wrong. The first casualty was the SS John P. Gaines on January 19, 1943. She broke completely in two while sailing off the coast of Alaska. 7 crew members died. The stern section sank immediately. The bow remained afloat long enough for survivors to escape. Then the failures accelerated. The T-2 tanker SS Esso Manhattan cracked her deck while in port. The SS Poneglyph split while sailing in the Atlantic. The Liberty ship SS Samuel Heintzelman suffered a complete hull fracture. Workers at shipyards began reporting cracks appearing in vessels still under construction, fractures radiating from welded joints like spider webs. By March 1943, over 1,000 ships had reported serious structural cracks. Nearly 400 suffered failures serious enough to take them out of service. 20 vessels broke completely in half. The catastrophic failure rate was approaching 3%. Unacceptable in peacetime, potentially war-losing under combat conditions. The United States Maritime Commission convened emergency investigations. Navy metallurgists examined fractured hulls. Shipyard engineers reviewed welding procedures. Insurance companies threatened to cancel coverage. Allied commanders watched their carefully planned logistics networks disintegrating as ships cracked apart faster than submarines could sink them. And in German technical journals, articles appeared noting the predictable failure of American welding technology.
German shipbuilding in 1943 remained firmly rooted in traditional riveting techniques. The Kriegsmarine's surface fleet had been largely destroyed or bottled up in port, but Germany continued building U-boats at an extraordinary rate, 40 submarines per month at peak production. Every one of them used riveted construction. German naval architects had experimented with welding in the 1930s. They understood the theoretical advantages. Welding was faster, created smoother hulls with less drag, reduced weight by eliminating overlapping plates, and formed continuous metal structures stronger than riveted assemblies. But they had also identified serious problems. Welded structures contained residual stresses from the heating and cooling cycles. The welds themselves represented zones of altered metallurgy, where the original steel's properties had been changed by melting and resolidification. Quality control proved difficult. A bad rivet was visible, but a defective weld might be hidden beneath paint or insulation. Most concerning, welded structures seemed prone to catastrophic crack propagation. A crack in a riveted hull would stop at the edge of the plate. A crack in a welded hull might race through continuous metal for dozens of feet. German engineering opinion considered welding suitable for certain applications, pressure vessels, structural steel, non-critical components, but inappropriate for ship hulls that faced the complex stresses of ocean service. The Americans' decision to build an entire merchant fleet using all welded construction struck German engineers as typically American, bold, crude, and ultimately foolish. Intelligence reports from the United States seemed to confirm German assumptions. The Abwehr received detailed information about Liberty ship failures through neutral channels. Swiss technical journals published articles about American welding problems. Swedish maritime insurance assessors reported alarming failure rates. German technical journals translated and republished these accounts, sometimes with barely concealed schadenfreude. A March 1943 article in Werft, Reederei, Hafen, a German maritime engineering journal, analyzed American welding failures. The author noted that the American preference for speed over quality has produced predictable results. Their welded vessels, constructed by minimally trained workers using questionable techniques, are failing at rates that vindicate traditional German engineering practices. The laws of metallurgy cannot be repealed by industrial enthusiasm.
What German engineers didn't understand, what nobody understood yet, was that the Liberty ship crisis was about to revolutionize material science in ways that would affect every industry using steel. Constance Tipper had never worked on ships before the war. A Cambridge-trained metallurgist and one of the few women in her field, she had spent her career studying the crystalline structure of metals. In 1942, the British Admiralty recruited her to investigate a disturbing pattern. Merchant vessels were suffering catastrophic failures in cold water. Tipper began examining fractured steel plates from damaged ships. What she discovered would eventually explain not just Liberty ship failures, but a fundamental property of steel that had been hiding in plain sight for decades. Steel, she found, didn't behave consistently across all temperatures. At warm temperatures, steel was ductile. It could absorb energy by deforming, bending, and stretching before breaking. But at cold temperatures, the same steel became brittle, fracturing suddenly with almost no deformation. The transition between ductile and brittle behavior occurred over a relatively narrow temperature range specific to each steel composition. This was the ductile-to-brittle transition temperature, or DBTT. Below this critical threshold, steel that seemed tough could shatter like glass. Tipper's findings reached American investigators in early 1943, just as the Liberty ship crisis peaked. A team of metallurgists from the Naval Research Laboratory, led by Dr. George Irwin, began systematically examining failed vessels. What they discovered was more complex and more frightening than anyone had imagined. The Liberty ships were failing through a perfect storm of metallurgical factors that nobody had fully understood before. The failures weren't caused by bad welding, at least not primarily. They were caused by the fundamental physics of how cracks propagate through continuous metal structures under specific conditions. First, the steel itself was vulnerable. Liberty ships used a manganese-silicon steel that seemed adequate when tested at room temperature, but its ductile-to-brittle transition temperature was around 40 degrees Fahrenheit. In the North Atlantic winter, hull temperatures regularly dropped to 30 degrees or below. At those temperatures, the steel became brittle, capable of fracturing suddenly instead of deforming gradually. Second, the welded construction created stress concentrations. Every welded joint represented a zone of altered metallurgy where the steel had been melted and resolidified. The welding process introduced residual stresses, internal forces locked into the metal structure by uneven heating and cooling. These stresses added to the operational stresses from waves, cargo, and ship motion. Third, and most critical, the all-welded construction eliminated crack arresters. In riveted construction, each steel plate was a separate piece, connected to adjacent plates by rivets. A crack that reached the edge of one plate would stop. It couldn't jump the gap to the next plate. But welded construction created continuous metal structures. A crack that started in one location could propagate through the entire hull without encountering natural barriers. Fourth, the Liberty ships contained geometric stress concentrations, sharp corners where hatches met the deck, square hatch openings instead of rounded ones, and abrupt transitions in plate thickness. These features acted as crack initiators, concentrating stresses at specific points. The investigators realized they were dealing with what would later be formalized as fracture mechanics, an entirely new branch of material science that studied how cracks initiate and propagate through structures. The Liberty ship crisis was forcing the development of theories and analytical methods that didn't yet exist.
By mid-1943, investigators had identified the problem. Now they needed solutions that could be implemented immediately across an entire fleet without halting production. The first fix was surprisingly simple: crack arresters.
Engineers designed small steel straps, riveted across vulnerable areas of the hull at regular intervals. These crack arresters interrupted the continuous welded structure, providing barriers that would stop crack propagation. If a fracture developed, it would run until it hit a crack arrestor, then stop instead of racing through the entire hull. Installing crack arresters on existing ships became a massive emergency program. Every Liberty ship in service was recalled for modification when possible, or had arresters installed at the next port of call. New ships received arresters during construction. The simple addition of strategically placed riveted straps transformed potentially catastrophic failures into manageable damage that could be repaired. The second fix addressed steel quality. Metallurgists identified steel compositions with lower ductile-to-brittle transition temperatures, steel that remained tough even in Arctic conditions. The Maritime Commission mandated new steel specifications for all future construction. Existing ships received supplemental steel plating in critical areas, using the improved materials. The third fix modified ship design. Naval architects eliminated or modified the geometric stress concentrations that initiated cracks. Square hatch corners became rounded. Abrupt plate transitions were smoothed. Highly stressed areas received reinforcement. These changes required modifying the standard Liberty ship design, but the alterations could be implemented without disrupting production. The fourth fix improved welding procedures. Investigators discovered that welding sequence mattered enormously. Welders had been joining hull plates in whatever order seemed convenient, but this created uneven residual stresses. New procedures specified exactly which welds should be made in which order to minimize stress concentration. Welders received additional training. Quality control became more rigorous. The fifth and perhaps most important fix was operational. Ships were instructed to avoid full-speed operation in heavy seas during cold weather. The combination of low temperature, high stress from wave impact, and hull flexing created the perfect conditions for catastrophic failure. By reducing speed and avoiding the worst weather, a significant change was made. By late 1943, the crisis was contained. The failure rate dropped from 3% to less than 1%. Catastrophic fractures became rare. Ships that had seemed ready to break apart at any moment returned to reliable service. The modifications worked. But something more important had happened. American metallurgists, forced to solve an immediate crisis, had pioneered an entirely new field of material science that would transform every industry using steel.
What emerged from the Liberty ship crisis was fracture mechanics, the mathematical framework for understanding how materials fail under stress. Dr. George Irwin at the Naval Research Laboratory developed the theoretical foundation during and immediately after the war, formalizing concepts of stress intensity, crack propagation, and fracture toughness. Irwin demonstrated that whether a crack would propagate catastrophically depended on the balance between the energy available to extend the crack and the energy required to create new fracture surfaces. This balance could be calculated, predicted, and engineered. Materials could be tested for their resistance to crack propagation. Structures could be designed to prevent catastrophic failure, even if cracks developed. The implications extended far beyond shipbuilding. Every industry that used steel, bridges, buildings, pressure vessels, pipelines, aircraft, automobiles, needed to understand fracture mechanics. The Liberty ship crisis had revealed that intuitive approaches to engineering design weren't adequate for modern high-stress structures. Rigorous mathematical analysis of failure modes was essential. Post-war bridge collapses, pressure vessel explosions, and aircraft accidents would repeatedly demonstrate the importance of fracture mechanics. The 1967 collapse of the Silver Bridge in West Virginia, killing 46 people, resulted from brittle fracture of a single eye-bar, exactly the kind of failure mode that Liberty ship investigations had revealed.
Modern bridge inspection and maintenance procedures trace directly to lessons learned from welded ship hulls in 1943. The nuclear power industry, which emerged in the 1950s, required absolute confidence that pressure vessels containing radioactive materials wouldn't fail catastrophically. Fracture mechanics provided the analytical tools to design and inspect these vessels. Every nuclear reactor pressure vessel is tested and monitored using techniques developed from Liberty ship investigations. The offshore oil industry, which began developing deep-water platforms in the 1960s, needed assurance that welded steel structures could withstand decades of cyclic loading from waves without catastrophic failure. Fracture mechanics made these massive structures possible. Modern aircraft design depends entirely on fracture mechanics. Every commercial airliner is designed with the assumption that cracks will develop during service. The question isn't whether cracks will appear, but whether they can be detected and repaired before they grow large enough to cause failure. This damage tolerance approach emerged directly from Liberty ship research. The welding procedures developed to save the Liberty ships became the foundation for modern welding codes and standards. The American Welding Society's specifications, which govern welding practice worldwide, incorporate lessons learned from catastrophic ship failures in 1943. Every welder trained today learns procedures developed to prevent the kind of failures that nearly destroyed the Liberty ship program.
By 1945, the Liberty ship program had produced 2,710 vessels, more than all other Allied merchant shipbuilding combined. Despite the crisis of 1943, only 3 Liberty ships were lost to structural failure during the war. Thousands more served reliably, carrying millions of tons of cargo across oceans under conditions far more severe than peacetime service. The welded construction that German engineers had mocked proved to be extraordinarily successful once properly understood and modified. Welded ships were indeed faster to build. The 70-day construction time for Liberty ships would have been impossible with riveting. They were lighter, with more cargo capacity. They had smoother hulls with better hydrodynamic performance. And once crack arresters were installed and proper steel was used, they were just as reliable as riveted vessels. German U-boats sank 200 Liberty ships during the war, about 7% of total production. But crack arresters, after the 1943 modifications, accounted for less than 0.1% of losses. The welding that was supposed to be the program's fatal flaw became its greatest strength. The German Navy, meanwhile, continued building U-boats using riveted construction throughout the war. German shipyards never achieved anything approaching American production rates. The Kriegsmarine commissioned approximately 1,150 U-boats during the war. Impressive, but far below the 2,710 Liberty ships produced by the United States alone, not counting other American merchant shipbuilding or Allied production. German submarine construction remained labor-intensive and slow compared to American methods. A Type 7 U-boat required approximately 300,000 man-hours to build, taking 6 to 8 months from keel laying to commissioning. A Liberty ship required approximately 200,000 man-hours, despite being far larger, and was completed in 70 days or less. The war ended before German engineers fully appreciated what American metallurgists had accomplished. Post-war technical exchanges revealed that German understanding of fracture mechanics had remained rudimentary. Their decision to avoid welding had been prudent given their knowledge, but it had also prevented them from developing the advanced material science that emerged from American crisis management.
Behind the statistics and technical achievements were people whose lives were changed by welding failures and by the solutions that prevented further tragedies. The SS John P. Gaines broke in two off Alaska on January 19, 1943. 7 men died in the engine room when the stern section sank in minutes. 31 survivors spent hours in lifeboats in freezing conditions before rescue. Several lost fingers and toes to frostbite. Chief Engineer John Graham, who survived, testified at subsequent investigations about the terrifying moments when the ship's hull cracked open with no warning. His testimony helped investigators understand the catastrophic nature of brittle fracture. The SS Schenectady broke while at dock, so no lives were lost, but the psychological impact on workers who witnessed a brand new ship simply crack in half was profound. Welders and shipfitters who had been proud of their work suddenly questioned whether they were building death traps. Morale in West Coast shipyards plummeted. Production slowed as workers demanded additional inspections and modifications. The crisis created opportunity for women in technical fields. Constance Tipper's metallurgical research, conducted while raising 2 children during wartime, directly saved lives and advanced science. Her work on ductile-to-brittle transition helped explain failures that male engineers had been unable to solve. After the war, she continued researching fracture mechanics at Cambridge, training the next generation of materials scientists. Thousands of welders, mostly women who had entered the workforce after Pearl Harbor, learned their trade under emergency conditions and found themselves blamed when ships failed. The popular Rosie the Riveter image celebrated women in shipyards, but when Liberty ships started cracking, fingers pointed at inadequately trained workers. The discovery that failures resulted from metallurgical properties rather than poor workmanship vindicated these workers and validated the emergency training programs that had brought them into industrial work. The Liberty ship crisis accelerated developments in materials science, welding technology, and structural engineering that continue reverberating today. Modern steel specifications include mandatory Charpy V-notch testing, a procedure that measures how much energy steel can absorb before fracturing at specific temperatures. This test, developed and standardized because of Liberty ship failures, ensures that steel used in critical applications remains tough under expected service conditions. Every steel shipment for bridge construction, pressure vessel fabrication, or pipeline installation is tested using procedures developed from 1943 investigations. Welding procedure specifications now require detailed documentation of welding sequence, heat input, cooling rates, and post-weld inspection. These requirements emerged directly from Liberty ship research, showing that identical welds could produce different results depending on procedure details. Non-destructive testing methods, ultrasonic inspection, magnetic particle testing, radiography became mandatory for critical welds because visual inspection couldn't detect the internal flaws that caused Liberty ship failures. The entire modern non-destructive testing industry traces its growth to post-1943 requirements for verifying weld quality without cutting structures apart. Fracture mechanics is now a required course for mechanical engineers, civil engineers, and materials scientists. The mathematical framework, developed by George Irwin and colleagues, forms the basis for designing everything from aircraft fuselages to natural gas pipelines. Computer programs that predict crack growth and structural life use equations derived from Liberty ship investigations. The concept of fail-safe design, structures engineered to survive even if individual components fail, emerged from the crack arrestor solution. Modern aircraft have redundant load paths, so damage to one structural element doesn't cause catastrophic failure. Ships have transverse bulkheads that limit damage from hull breaches. These design philosophies reflect lessons learned when simple riveted straps proved capable of stopping catastrophic cracks. The greatest irony of the Liberty ship crisis is that welding, the technology German engineers dismissed as crude American corner cutting, became the foundation for post-war shipbuilding worldwide. By the 1950s, every major shipyard had converted to all-welded construction.
Riveting survived only for specialized applications. German shipyards, rebuilt after the war, adopted welding techniques pioneered by the Americans they had mocked. Modern German ships use all-welded construction, incorporating fracture mechanics principles developed from Liberty ship failures. The Mercedes-Benz automobiles, Siemens turbines, and ThyssenKrupp steel structures that exemplify German engineering today all depend on welding procedures and material science that emerged from the 1943 crisis. The Liberty ships themselves, built as emergency wartime expedients with expected service lives of 5 years, proved remarkably durable. Hundreds remained in commercial service into the 1970s. The SS John W. Brown, built in 1942, still operates today as a museum ship in Baltimore. Her welded hull sound after more than 80 years. The SS Jeremiah O'Brien, launched in 1943, returned to Normandy for the 50th anniversary of D-Day in 1994 under her own power, a voyage that would have been impossible if the welding that German engineers mocked had actually been as flawed as they claimed. In 2024, nearly all large ships use all-welded construction. The methods are more sophisticated than 1943 procedures, but the fundamental principles remain the same. Modern container ships, tankers, and cruise vessels exist because American metallurgists and engineers, facing a crisis that threatened to lose the war, developed the science and technology to make welded structures reliable.
The Liberty ship crisis teaches lessons that extend far beyond shipbuilding or even engineering. It demonstrates that crisis can drive innovation faster than peacetime research. It shows that apparent failures, properly investigated, can become breakthroughs. It proves that the crudest solution, thoroughly understood and correctly applied, can outperform elegant alternatives. Most importantly, it reveals that engineering progress doesn't come from avoiding problems, but from confronting them honestly, studying them rigorously, and developing solutions based on fundamental understanding rather than intuition or tradition. German engineers mocked American welding because it violated their understanding of proper practice. They were right that early Liberty ships suffered serious problems, but they were wrong about the ultimate outcome because they didn't anticipate how quickly American engineers would learn, adapt, and innovate under pressure. The Americans who built Liberty ships weren't better trained than German engineers. They didn't have superior theoretical knowledge. What they had was urgent necessity, industrial capacity, and willingness to learn from failure. When ships started breaking apart, they didn't abandon welding and return to riveting. They studied the failures, understood the causes, developed solutions, and emerged with knowledge that transformed their industry and every field that worked with steel. 2,500 Liberty ships that should have cracked apart instead carried armies across oceans, transported supplies that kept Britain fighting, and delivered the industrial might that won the war. They succeeded because American engineers refused to accept that welding couldn't work. They made it work, and in the process, they revolutionized materials science. The ships that German engineers said would fail became the fleet that won the Battle of the Atlantic. The welding technology they dismissed as crude became the standard that everyone, including Germany, would eventually adopt. And the crisis that nearly destroyed the program became the foundation for engineering knowledge that protects millions of lives today every time someone crosses a bridge, flies in an aircraft, or benefits from any of the countless structures whose safety depends on fracture mechanics. That is the ultimate answer to the mockery. Not words, but 2,710 ships that proved welding could work and the lives saved by the science developed to make them safe.